This lesson is on hybridization. So previously we studied that chemical bonds are formed when unpaired electron orbitals overlap, resulting in both sigma bonds and pi bonds, depending on how the orbitals overlap. And this is called simple valence bond theory. Unfortunately, this theory was unable to correctly predict the experimentally determined shapes and bond angles of more complex molecules. So for this, we have to turn to a concept called hybridization. So I'm going to skip around and I'm going to take a look at what this is right here. This is the energy level diagram for carbon. So this is carbon's valence shell right here. I'm going to put C there for carbon. C, and then the valence shell is 2s2, 2p2. If we were to look at this, we see only two atomic orbitals with a single electron. This would suggest that carbon could only make two bonds, since it only has two orbitals available for overlap. We know this is not the case. We know that carbon forms four bonds. So what in fact happens is that one of these electrons right here gets promoted to an empty p orbital. So it undergoes electron promotion. And then we have S and three p's. So we have an S with one electron, and we have three p's, each with one electron. This makes sp3 hybrids, so each of these atomic orbitals becomes an sp3 hybrid. It's not that this is an S and these are p's and these are p's. Each of these, this is an sp3, this is an sp3, and there are four of them. So they all combine and they make sp3 hybrids. They look like this, okay? So they've got a big lobe because they're incorporating part of the S features, and then they also have these two lobes because they are also incorporating features of the p orbitals. So we have, in this case, there are four of them, and now that they all have one electron in them, carbon is able to make the four bonds we know it is capable of making. The resulting orbitals arrange themselves in an orientation that is called tetrahedral. All right, so what we see here is we have one sp3 going up, one sp3 coming to the side, one forward, and one behind. Then the hydrogens then overlap on each of these, all of those making sigma bonds. Okay, and we get a molecule of methane. And methane looks like this when we draw it with its stick and wedge diagram. So we have one hydrogen coming up, one hydrogen along the side on the same plane. We do a triangle for a hydrogen coming forward, and we do a dotted for a hydrogen going backwards. Important to note that these three hydrogens should be pointing down. And this hydrogen is going up, and the bond angle here is 109.5 degrees. And that bond angle is the same for each of the hydrogen-carbon-hydrogen bonds. Okay, and so what we have right here is we have a stick representation of what we see as a molecule right here. I'll bring this up right here. So we've got the hydrogen going up, the hydrogen coming to the side, so these two are on the same plane. Then you've got the hydrogen coming forward, and the hydrogen on the back, that's the hydrogen in the back. So these are important aspects to understand about hybrid orbitals. Each orbital is identical. So each of these sp3 orbitals is identical to each other. They are the mathematical average of the atomic orbitals. So they're 25% S in character and 75% P in character. That's for an sp3 orbital, right? Because there's four parts to it. So a quarter of it is S and three quarters of it is P. They possess the average energy of the orbitals used to form hybrids. So all of these three orbitals are at the same energy level, and they have the average energy of these ones, of the S and the P's. And hybridization takes place using the orbitals within the same principal quantum number. Okay, so these are important aspects just to know about the hybrid orbitals that form. We have a procedure for hybridization, and what I'm going to do is I'm not going to go through the procedure right now. I'll go through it as we look at an example. But when we form hybrids, we get different geometric shapes. So if only an s orbital and only a p orbital hybridize, we get two sp2 hybrid orbitals. And two sp2 hybrid orbitals look like this. So we've got one that looks like this. This is an sp2, or sorry, this is an sp, and then we've got an sp right there as well, and then they overlap, as you can see right here. They're overlapping, right, and they create 180 degrees, and so the shape right there is linear. All right, so we've got, this is my wedged and dotted line diagram. A is the central atom and X is the surrounding atoms, and the bond angle is 180 degrees. If you have an s orbital with a p orbital and a p orbital that's hybridizing, we get sp2 hybridization. There's 3 of them, and that's called trigonal planar. It's called trigonal planar because it's basically a triangle on a plane. It's easy to see like this. Okay, and so these all of these atoms sit on a plane, and they all have a bond angle of 120 degrees. This one was 180 degrees. Okay, tetrahedral we just saw, and that's when you have S, P, P, and P all hybridizing to form sp3 hybrids. There's 4 atomic orbitals of sp3, or 4 hybrid orbitals, and they form a tetrahedral shape. This is shown as follows. You've got your central atom, you have one coming up and one to the side. These are on the same plane. And you have one coming forward and one going backwards. Now, the challenging ones that we'll see right here are the ones where a central atom is able to form more than 4 bonds. And that's when we involve the d subshell in our bonding. So if one d orbital and an s, a p, p, and a p all hybridize, we get 5 dsp3 hybrid orbitals, and they make this trigonal bipyramidal shape. And the reason why it's called trigonal bipyramidal is because there is a triangular based pyramid on the top. You can see this right here, triangular based pyramid on the top. And there's also a triangular based pyramid on the bottom. So it's bipyramidal, 2 pyramids, one on the top, one on the bottom, and the central atom is in the middle. There is a trigonal plane that sits right here. I'm not sure if you can see that. I'll shade it in. And so these 3 x's right here all sit on a plane with the central atom. And then there is an x that, or an atom that's above and an atom that's below. We draw this with a wedge diagram as follows. We have A, X, X. These are the ones that are on the top and on the bottom. Then we have the X coming forward and an X going backwards, like this. And this is what we do to draw that trigonal plane that's in the middle there, that I'm also going to try and shade for you right here. Okay. You can see that the angles on that trigonal plane, right, are similar to trigonal planar, right? They're 120 degrees. So this is the formation that's on the trigonal plane right here. So this right here is 120 degrees, and this right here is 90 degrees. So these make 90 degrees to the plane, and then on the plane, the atoms make 120 degrees to each other. The next one is octahedral. Octahedral, as you can see, is 2 square-based pyramids. We call it octahedral because there are 8 faces in this molecule, or it creates 8 sides in this 3D molecule. So we have a square-based pyramid on the bottom, okay, and then we also have a square-based pyramid on the top, okay, and then we have a square plane in the middle here. This results when you have 2 d atomic orbitals that hybridize with an s, a p, and a p, and you get d2sp3. And there's 6 orbitals that form there. Okay. Now this might all seem confusing, but once you start to see examples, you'll notice that it actually is not as challenging as it seems initially. Okay. Bond angles here are 90 degrees, and they're all 90 degrees right here as well. When we draw Lewis diagrams, we're going to be using this procedure right here. It's called beyond the octet rule, and it's basically like electron bookkeeping. We look at the valence electrons, we count up all the valence electrons, and then we make the bonds to the central atoms, and then we make double or triple bonds as necessary. So I'm going to go through this procedure right here for the hybridization of methane. So let's look at our examples, or let's look at our procedure. What I'll do is I'm going to screenshot our procedure here, and what I'll do for hybridization is I will just have that procedure nearby so we can see what we have to do next. Okay, so you can see in step 1 that I have to draw the Lewis structure of that diagram, and I'm going to use this procedure right up here beyond the octet. So what I do is I decide which ones are the central atoms, and then I count all the valence electrons. Carbon's going to be my central atom. It has 4 valence electrons. Hydrogen are going to be around it, 1 electron, and there's 4 of them. So I have a total of 8 electrons to place. Carbon is going to go in the middle. I'm going to put the hydrogens around it. And now I'm going to start placing electrons. Here's a bond, that's 2 electrons. Another bond, 4, 6, 8. So I've completed the Lewis structure. That is step 1 of the hybridization process. Now you might be wondering, well, I know a different way of doing this. Comes up with the same structure, and it seems a lot easier than this convoluted method. The only thing I would say is that the method that we use here helps us more accurately draw diagrams than most methods that I have come across for Lewis structures. So I would really suggest following this method here because it will help us when we get to more complex structures. All right, so step 2. Step 2 says draw the valence shell of the atoms involved in bonding. Okay, so let me do that. So step 2, the valence shell of the atoms. Carbon right here is 2s with 2 electrons, 2p, okay, and we saw this before. It looks like carbon could only form 2 bonds. We know it doesn't. We know that it forms 4. And then you have hydrogens. You have 4 of them, and they all have 1s valence shells. Okay, so there you go. That's my step 2. Step 3, promote electrons on the central atom if necessary to meet the number of bonds of the Lewis structure. Well, the Lewis structure has 4 bonds, and this looks like it can only form 2. So what I'm going to do is I'm going to promote electron from here to here. I'm going to erase this electron right here. I'm going to write that this is step 3, electron promotion. And I'm doing this because it is necessary. Okay, so now I've got S, P, P, and P. Okay, so I know that I'm going to form 4 sp3 hybrids. Step 4, reserve any p orbitals if there is or are double or triple bonds. Step 4, we're going to skip because we don't have any double or triple bonds. So that's skipped. The reason for that is we have no double or triple bonds. Okay, I'm going to move this over to this, just down here. 1 second. Okay. And it says step 5, hybridize the occupied orbitals of the central atom. So let's write that up here, step 5. My hybridization is S plus P plus P plus P. So I'm going to get sp3 hybridization, which forms a tetrahedral structure. So I get 4 orbitals on carbon, and each of them are sp3 hybrids. As we can see from this diagram now, they all have 1 electron in them, so they're able to form 4, carbon's able to form 4 bonds. And I've got my hydrogen, 1s. I've got another hydrogen, 1s. I've got another hydrogen, 1s. I've got another hydrogen here, 1s. Okay. Now, step 6. Show overlap of orbitals using the energy level diagram, so 6a. So I'm going to do step 6a right here. Okay, well, these are going to overlap. These are going to overlap. Okay. All right, so as we can see here, I've got my 4 bonds. Each of the sp3 hybrids are overlapping with a 1s orbital. Okay, I'm going to just scroll down just a little bit here, and it says I'm also going to using labeled orbitals. So what I'll do right here for that is I will put carbon in the middle. And remember that it forms this tetrahedral structure of sp3 hybrids. So these two are on the same plane. Then there's one that's coming forward. And then there's one that is behind. So hopefully that diagram there is a good 3D diagram that shows sp3 hybridization in a tetrahedral structure. What overlaps here is the 1s of the hydrogens. So that's my hydrogen 1s. And as a result of this overlap, I get a sigma bond on each of these areas of overlap between the sp3 and the 1s orbital. The final thing is step 7, draw a shape of the molecule using a 3D structural formula. Okay, so let's bring this over here. I'll do a 3D structural formula right here, step 7. I have my carbon. Okay, and I'm drawing my hydrogens, and I'm going to indicate that the bond angle between all of these is 109.5 degrees. Okay, there should be a next video that shows the other two examples in this lesson, so check that one out as well. Thanks.